Welcome to this second lecture on ideal fluid flows using complex analysis. Now, recall that in the previous lecture we looked at the concept of the velocity potential and how the velocity potential satisfies the Laplace equation. So, we had defined a variable or a function phi which is governed by the equation del square phi is 0. So, in this lecture I will talk about a second complementary function which is stream function, and then I will discuss the concept of orthogonality of streamlines and equipotential lines. So, to begin, let us consider a 2D flow and let us say this flow is irrotational. Now, in this 2D flow we can write the velocity vector u to be either say u I cap plus v j cap, or I would use a shorthand notation where I would write this as u comma v. Now, for an ideal fluid we know that this flow field must satisfy the continuity equation which was del dot u is 0, which if you use in a vector sense will be du dx plus dv dy is 0. Now, what I will do is I will define a new function which I am going to call as psi, and I am going to call it the stream function. So, we will define this new function psi which is a stream function, but it is given in a very specific form. It is given in the following manner. Say I define u to be d psi dy and v to be minus d psi dx. Now, if the function psi is twice differentiable, so we can say if psi is twice differentiable, which would mean we can take two derivatives, especially the mixed type with this function, then we can see that if I plug in these notations now into the continuity equation, what we will get now will be d by dx of d psi dy plus d by dy of minus d psi dx, which would be d2 psi dx dy minus d2 psi dy dx, which is 0. So, this function psi, or this formulation of taking velocities components in terms of the function psi, which is the stream function, is such that in the 2D flow it automatically satisfies the continuity equation. Now, though this function psi has nothing to do with flow rotationality or irrotationality, so this function psi would also be valid for a rotational flow in 2D flows. But for the purpose of this course, because we are dealing with ideal fluids, we will be stressing again and again on irrotational flows, and so our focus will be on deriving properties of this function for irrotational flows only. So, we will limit ourselves to the usage of this function psi for the case of irrotation flows. Now, recall that vorticity, which I denoted by the symbol omega vector, which would have three components. Let us say the three components are the following. We have xi, eta and zeta as the three components of the vorticity vector, which I could write as, for instance, xi I cap plus eta j cap plus zeta k cap. Now, the only non-zero component of this vorticity function or this vorticity vector in 2D coordinates or in 2D flows. It is easy for you to work it out, and I am sure you would have also covered this as part of your undergraduate fluid mechanics, that in 2D flows the only non-zero component or the single component that would be possible to derive would be zeta, which would be given as dv dx minus du dy. Further, if I was to say that the flow is irrotational, so going beyond even the definition, if I say that the flow is irrotational, what it means is that zeta should also be 0. That is the only way the flow can be irrotational. What it means is dv dx minus du dy is 0. Now, what I am going to do is I am going to substitute the definition of the velocity components u and v in terms of the stream function. So, we will say u is d psi dy and v was minus d psi dx. So, if you plug it into the definition of zeta, we get d by dx of minus d psi dx minus d by dy of d psi dy to be 0, and then if we take it one step further, we will get minus of d2 psi dx square plus d2 psi dy square is 0. Well, the negative sign is immaterial, so let me just cancel it off. So, what we get is in 2D flows del square psi is 0 if the flow is irrotational. So, this very important result that we have derived now is that for irrotational flows, just like the velocity potential, the stream function also satisfies the Laplace equation. Just like phi, the stream function, which is psi, also satisfies the Laplace equation. And this is going to be again a very important tool for us in the following lectures. Now, let me state one key fact here, and then we will try and prove it using the definitions that we have come up with so far. The theorem that I am going to put up is, or the fact that I am going to put up are, or is that flow lines corresponding to a fixed value of psi. So, for instance, say psi is some constant. So, flow lines corresponding to a given value of psi are streamlines of the flow field. So, if there is a line over which psi is constant, then that line is going to be a streamline of the flow field, and we can easily prove this by the definitions that we have come up with. We could say d psi, the total change in psi, could be written as d psi dx dx plus d psi dy dy. Now, note that d psi dx is minus v and d psi dy is u. So, we can write this as u dy minus v dx. Now, let us consider the case that the stream function is a constant. So, if psi was a constant, then d psi must be 0, or the change of psi on that line must be 0, which gives us u dy minus v dx over this line psi equal to constant must be 0, which if we do a little bit of rearrangement now, you can see that dy by dx for a constant psi is given as the ratio of the two velocity components. So, v by u. Now, this is precisely how the streamline is defined. If you recall, we said the streamline is an imaginary curve, the slope of which or the tangent to which gives us the direction of the velocity vector. So, it is this which is the slope of the streamline, and so we can say that psi being a constant corresponds to a streamline. Furthermore, each value of that we assign to a streamline, each unique value means or pertains to a new streamline. So, hence we get the name stream function. That is the whole idea why this is called as a stream function, that this function can take a range of values, and for each value or each unique value you get a unique streamline. So, now let us consider a scenario where we have two streamlines in a flow field, say psi equal to psi 1 and psi equal to psi 2. And let us define a coordinate system as well. So, let us say we have x here, y here. So, this is a 2D flow field. Now, the question that I am going to pose is the following. I want to know the flow rate of the fluid flowing between these two streamlines. Note that we had said earlier in the previous lecture, we said the dot product of the velocity field with the normal vector on a streamline is 0. So, that means that there must be no mass flow rate across a streamline. So, between these two streamlines there must be some fluid that is flowing, and we want to quantify how much is that flow rate. So, what we will do is, say we take any 2 points A and B, A on streamline psi 1, B on streamline psi 2, and let me draw a convex surface connecting A and B. So, say we take a surface which has the following shape, and the shape is chosen specifically so that the slope on this surface is always positive. That is just for convenience. We could have chosen some other surface as well, but just to make a point, just to prove it quickly, let me say this is what I am going to choose. Okay, so, it is a curve, this line AB is of arbitrary shape, but it is such that it has a positive slope. For all we care, it could even be a line connecting A and B, a straight line, but for now let us just take a curvilinear section. Okay. What we want to determine? We want to determine the following quantity. We want to know what is the flow rate across this line AB, and that would be given by this function q. And let me now show you what q is. So, basically if we take a small element, and which I am going to represent by a large element here for only for the purpose of for visual clarity. If I take an element which has a length of ds along this curve AB, say we are going from A to B. So, anyway the ds will be pointing from A to B. The normal vector to this point would be in this direction, and that is a unit normal, which means modulus of unit normal is 1. If I can decompose the flow at this location, I could say this is for instance the x component of velocity, this is the y component of velocity, u and v. I am interested in knowing what is the flow rate across this element, small element, infinitesimal element ds, and that too per unit depth. So, this is the volume flow rate of the fluid flowing across AB per unit depth. And that is what we are trying to calculate. Now, it can be easily proved, and which I am going to not prove here, but you can easily work it out, that the normal vector, or in fact the normal vector times ds can be easily written as dy I cap minus dx j cap, where dx and dy are the lengths when you project ds along x and y direction. So, knowing this, let us calculate q. So, q would be, now remember it is u dot n ds. So, clearly u dotted with n ds would now be u dy minus v dx. So, u dot n ds will be u dy minus v dx, and now we can integrate over the path a to b. So, we will get u dy minus v dx as the integral from a to b, and now I note that u dy minus v dx is the total change in the stream function. This comes from the definition that we had written right here. So, if you see this, this is what we are using now. So, we are using this definition of d psi. So, we can plug this in, and then we know that it is a total change in psi. So, that must be psi at b minus psi at a, which would be psi at b is psi 2 minus psi at a is psi 1, and so the total flow rate per unit depth between any two streamlines is the difference in the stream function values, and that is the significance of the stream function. So, we can calculate the volume flowing between any two streamlines by the difference between the stream values or the stream function values. Okay. Now, let us consider the we go back to the velocity potential, and let us look at a specific relationship between velocity potential and stream function. Now, recall that velocity potential was phi and gradient of phi was u, which is basically u comma v. So, clearly u must be d phi dx and v must be d phi dy, that is just from the definition. So, let us consider the total change in the function phi. So, d phi would be d phi dx dx plus d phi dy dy, which we can now write as d phi dx being u, I can write this as u dx, d phi dy being v, we can write this as v dy, and we can now say that if I am on a curve on which phi is a constant, on a curve on which phi is a constant would mean d phi on that curve would be 0. What it means is that u dx plus v dy on this specific curve where phi is a constant is 0 if there is a curve in space of that type, which means if we rearrange again, we can prove that dy dx for this curve where phi is a constant is minus u by v, which I could also write as minus 1 by v by u. So, I want you to put this specific result in perspective from what we have done just a little while ago, which is to talk about the stream function. So, together with what we have done here, which is to prove that the slope of the stream function or slope of the streamline is given as the ratio of the y component of velocity to the x component of velocity, we now see that for a stream or for a potential function or for a potential flow problem, a curve on which phi is constant, the slope is given by the negative of the x component of velocity versus the y component of velocity. If you recall from coordinate geometry, if there are two lines across which, let us say, the two lines have slopes m1 and m2, the condition that these two lines are orthogonal to each other would be that m1 m2 is minus 1. The same thing has happened here, that if you look at the slope of the line at this specific location on a given value of velocity potential, then that is negative 1 by or negative inverse of the slope of the line which is given by the constant stream function. What it means is that streamlines and equipotential lines, by equipotential we mean lines where the potential is a constant, are mutually orthogonal or are orthogonal to each other. So, this will also be very handy when we start drawing flow diagrams in the next few lectures. So, I will finish this lecture here and I will hope to see you in the next lecture. Thank you.